it. Now it works.
You should be able, so far it's been okay.
Yep. Can you see the screen?
Yes, so start when you want to. Thank you.
Great, okay. So hello everybody, I'm Joosep. I will be talking about how to do physics analysis on a GPU using all the great technologies that have come out of this PyHEP working group, particularly awkward array, and how to connect this to technologies such as numba that you already heard about, and also QPy from more of the data science world. Now, a caveat I want to stress is that this is mostly work done essentially late last year, before all the great developments came out, in particularly awkward one or nano events, some of which we have already heard about today, and you will hear about later in this workshop. So this is some kind of a wrap up of some older work, and perhaps is not making use of the latest and greatest technologies, but sort of demonstrates how one can tie all these different ideas that allows us to use also accelerators for physics analysis. So I put this up on Google Colab. You can also open this on your own. You will need a Google account. I will upload also a version with the results evaluated onto GitHub later on, but is the only place where you can easily get access to a GPU without a lot of hassle. So that's one of the sort of organizational aspects. So if you are running it on Colab, go ahead and switch to the GPU runtime. So go to runtime, change runtime type, and just make sure you got a GPU. And then save, and you will restart. For me, it's already done. So we can see that I have a GPU available. It's a Tesla P100, which is a kind of high-end GPU. So none of which I show here is particularly specific to NVIDIA GPUs, although we do use CUDA. So just technologically, we use this library, but we don't sort of hyper-optimize this or anything. So numba itself does support in more recent versions also AMD ROC, which I have not tried myself, but it should. There is a NumPy analog for AMD GPUs, but nothing prevents something like this to be developed. So let's go ahead and download an open data file for local use. And this will take a few minutes. And while it's downloading, I'll just go over the things I will sort of show today. So I'll just show a very simple way you can load this file and get the awkward array content. I think most of you are already familiar with this from the prior tutorials, from prior experience. Unfortunately, I could not participate in the earlier session, so I don't know exactly what was discussed, but I will definitely go over this later on. Then I will show how you can compile a custom CUDA kernel with numba, just in a sort of very simple entry-level way. I want to stress that we don't do any specific GPU optimizations, which can get quite technical. This is really aimed to be a sort of entry-level tutorial, and I'm sure there are people in the audience who are much better versed in all the intricacies of GPU coding than I am. So this is more like a physicist's way of tying things together. Then I'll show how you can use the multi-threaded aspect of GPU programming to process a simple array with threads in these CUDA kernels. And then I'll show how to create a kernel to process jagged array events, which is something that Awkward does for you, but sort of as a way to really illustrate how to do this by hand. We do this by hand. Then I'll show how to write the CUDA code to do some typical physics tasks. For example, computing the invariant mass of a jet and filling a weighted histogram. Is there a comment? No. And then to tie this all together, I'll show, just as an example, one of the exercises from the analysis description language sort of benchmarks, which are aimed to be sort of more complicated analysis tasks that cannot be accomplished with a one-line NumPy call, but which needs some sort of more complicated processing. So we will essentially do a jet to lepton delta R matching, compute the sum pt of the jets that are not matched to leptons, and then fill a histogram. Okay, so our file is still downloading, but okay, so then I'll just discuss a little bit more. So in case you are not familiar, here is a sort of 1 minute intro to GPU kernels or CUDA kernels. We execute these functions or kernels in many simultaneous threads. So the GPU is essentially a thread processing device. And each thread runs independently, but may share certain registers on the device, which means that certain threads may run in lockstep with each other due to the hardware limitations. So it's somewhat of a more restricted model than a CPU. And each thread gets indexed by block and thread indices, which essentially allow you to assign a chunk of work to a thread based on the indices. So here on this image, you see a grid which is made up of blocks, and each block is made up of threads. So you assign to each thread a piece of work, and then you write the code that the thread is supposed to do, and then you say how is the data supposed to be divided up into threads and blocks. So in this case, we have a two-dimensional grid. This can be 1, 2, or multidimensional in CUDA, and this should kind of correspond to the dimensionality of your data. In this case, we have a two-dimensional grid of blocks and 2 dimensions of threads in block. As mentioned, we will not be going into the technicalities of the GPU programming. We will kind of use them in a somewhat naive way, which nevertheless allows you to speed up the processing with respect to the CPU quite a bit. But in going into the details, the threads that run in the same block kind of run in lockstep because they get executed by the same GPU core, which is in NVIDIA parlance called a symmetric multiprocessor. And each of these SMs consists of many CUDA cores. So if you see some marketing material saying that the GPU has many thousands of cores, just keep in mind that these cores are not the same cores as the ones in your CPU. Okay, let's check. So the file is almost there. I do download this file kind of locally by hand just to not have to pay the HTTP access cost all the time. But thanks to uproot, of course, you can access this file or these kind of files directly from your code as well without downloading locally. And then, of course, you have to do some caching. So it's going to take a minute longer. So let's see. I don't use any other libraries here except numba and QPy, which are already installed in the runtime. So we don't use any custom libraries here today. Everything is installable from pip and things you should already be familiar with. And just to get this out of the way, in order to help with the debugging of the CUDA kernels, we need to print out stuff from the kernel using familiar printf stuff, but they are not captured well by the Jupyter notebook. So we have this little hack here that just allows you to wrap the output from the notebook. So this is just a pure technicality. So okay, let's get started. Our file is downloaded. Let's load the file and have a look what's inside, which branches. So you see here there are muons, electrons, taus, met, and jets. So this is the familiar jagged arrays that we are all very glad to use these days. And let's load a couple of the jet properties into memory. So now into the host or CPU memory, if you will. So we can just see what we have. So we have jetpt, a jagged array, which for each event we have a number of jetpt values. Okay, great. That's all very good. So now let's go ahead and create the first CUDA kernel. So what we need to do is we need to do from numba import CUDA, and then CUDA.jit allows us to JIT compile Python code into CUDA code. So this works the same way numba compiles fast code for the CPU, that it essentially kind of looks at the Python code and it translates it into the relevant device code. So not everything is supported, that's the bottom line, only a limited set of operations. So you cannot do complicated dictionaries or anything like that, but you can do arithmetic. So here's our simple example kernel that takes as an input an array, and as an output has also an array for which the memory has already been allocated. And for the moment, we don't do anything in this kernel. We just print out our location in the CUDA hierarchy. So we print out what is the index of the block. So if we go back to this, if we go back to this block image here, then which of these blocks are we in with this thread? And then we have a thread index, which says which thread in this block is currently being processed. So we have a block index, a thread index, and then we have also the block dimensions, which just says how many blocks are there in total. And in order to run this kernel on the GPU from Python, you don't need to do anything more than call it with these square brackets and specifying the number of blocks and number of threads you want to create. And the kernels themselves run asynchronously from numba CUDA, which means that they basically return immediately, which allows you to kind of schedule many independent things and then wait for all of them to finish at once at the end. So if we want to just wait for all the open kernels to conclude, we need to call the following, CUDA synchronize. So let's get the first 10 PT values from the events, kind of neglecting the awkward array structure at first. So just taking it as a flat array. And then let's create an output array which is of the same size and same type as the input array. So an important thing to keep in mind for CUDA programming is typically the devices are single precision, or they have many more single precision processors or operations available than double precision. So you want to make sure that all your computations first would work fine in single precision, and that they actually use float 32s, not float 64s. You can otherwise really slow down the code kind of unexpectedly. So now let's run this kernel or this function in a single thread. So we specify block size 1 and 1 thread, and just put the same arrays. So great, it ran, it did its thing, but we don't know what's going on. So as I mentioned, to catch the std out printout in the Jupyter notebook, we need this wrapper function. So let's just do that. So you see, we ran it with 1 block and a single thread in that block, and that's what gets printed out. So this thing gets called just once with a block index 0, thread index 0, and block dimension 1. Now let's run 5 threads, but one block. Then this line gets called out 5 times. So all of these get executed in parallel, and essentially CUDA kind of synchronizes the printout for us, that they don't get all mixed up, and we see our output as we expect. If you remove the printout, then of course every thread kind of runs in its own time. Now let's run 2 blocks, 5 threads each. We would expect 10 lines. And that's indeed what we get. Okay, so that's kind of the very basics of a CUDA kernel. If you've never written one before, that's how you do it. So I don't claim to be a CUDA programming expert, but that's kind of how I got started. So now let's go ahead and use this to process an array. So we have our example kernel here, which again takes an input array and an output array. And now we use the block and thread indices to to create an array index, just kind of scanning to the right place. And then we do a simple transformation on this input array, just multiplying it by 2. So we take the corresponding element from the input array, we multiply it by 2, and we put it in the output. And for debugging, we also print out the same stuff as before. So we also print out here the index in the array. So let's go ahead and run that. And let's zero the output just to be sure. And let's run that with 2 blocks, 5 threads. So now we see our familiar printouts. We see that the array index goes from 0 to 9. So we kind of deal with all the inputs. If you remember the input array, we chose exactly 10 elements at this moment, and we see that the output is double the input. So great, that's what we would have expected. Of course, there is a much easier way to do this simple multiplication as well with QPy, but here we go. That's how you can write the kernel to process array data. Now, this requires you to choose the block size and number of threads exactly for the size of the array, which is not very convenient if you want to process millions of events. Numba has helper functions for this to simplify the thread and block indexing. So let's use numba CUDA grid and grid size to create this xi and xstride values. And we have this pattern, which is kind of just a cookie cutter way of looping over the array elements in CUDA using the grid properties. So here, each thread processes a part of the array such that all the data is split up among all the threads. And let's run that on the same input, so the 10 element array with 2 blocks and 2 threads. So now we see thread 0, thread 1, block 0, block 1, but array index goes from 0 to 9. So we can process the whole array. Okay, great. So now we can process sort of flat homogeneous array data. Now let's go on to the jagged data from awkward array. So suppose we have this same JetPT array as before. Thanks to awkward array, we can compute the per event sum PT in a very idiomatic and straightforward way using jetpt.sum. So this returns for each event the sum of the per event JetPT values. Now QPy is basically a drop-in replacement for NumPy for the most part that runs on a CUDA GPU. So for simple and universal array functions such as like sine, cosine, square root, we can compute this directly using QPy in the following way. So we first have to transfer the data into the GPU memory using QPy.array, giving the NumPy array, and then we can just call QPy functions on the data. So here we compute the px from the pt and phi. And there we go. So that works fine. So you can use QPy without even knowing really that you're running on a GPU. Now we can also compare the speed of this GPU and NumPy, where NumPy is, I think, running single-threaded, but it's kind of hard to tell sometimes. So let's do time it for the NumPy. Okay, it's like 100 milliseconds per loop. And time it for the QPy, it's less. Okay, so great. It's faster for this particular operation, stressing that we did not allocate memory on the GPU inside the loop. So of course, memory allocation is slow, so you want to avoid that if possible. I see some chats, but I don't see what's written in the chat. So in case there is something important, please speak up. Okay, so now how about computing these event-wise quantities with jagged arrays on a GPU? As you saw on a CPU, thanks to Awkward, it's very simple. Now, Awkward 1, as I understand, has support for GPU kernels, but I have not used it yet. So I'm not familiar how to do that. In this example, I will show how to do this manually with numba, which shouldn't be taken as the recommended way to do it. It's purely for illustration or as a stopgap before Awkward 1 is in wide use. Now we can interpret this one deep jagged array using basically the content, which is the float 32 data of all the JetPTs, and the int64 offset array, which says what is the sparsity structure of the data. Again, I stress that this is specific to the old version of Awkward, and this will be different in Awkward 1. So we write this simple kernel that takes as an input the offset array, the content array, whoops, this should be float 32, and an output array, where the output is per event, but the content is per jet. And we have, again, this array looping sort of example. Let me just check the chats real quick, because I'm worried that maybe I'm muted or something.
No,
Okay.
it's mostly
No.
the banter.
Everything's fine. Everything's fine. Okay. Yeah. So we rewrite this example kernel to do the same sum as Awkward does for us here by hand, just to be able to run that on the GPU. So we loop over the offsets, basically over each of the events, and then for each event we get the start and stop indices of the jets using the following. And then inside each thread, we loop over all the jets, and we add up the JetPTs, or whatever the quantity was that we want to add up to the output. Now, one has to be very careful with this kind of code, because of course there is the possibility of race conditions. If you write from multiple threads into the same array location, then things will get messed up. However, here each thread gets one event or one array location, so we are safe from race conditions in this case. So let's run that. So now we want to compute the sum PT of the jets in the events using the GPU. We copy the data to the GPU first, so the JetPT values and the offsets, and we create an output value for the number of events that we know we have. And then we call the kernel with the following block and grid size, and we call the CUDA synchronize right after, just to get the output. All right. So here we have our some PT values, and you can see that they are the same. Of course, expect some small numerical differences, as you see here, because of things like floating point order and so on and so forth. But essentially, one can verify the CPU code with respect to the GPU code. I didn't mention, but if you just remove the CUDA JIT and essentially change this part here, which is kind of boilerplate, then you get CPU code that numba can speed up as well, using also parallel sort of built-ins. Okay, so let's time that too, just for fun. I mean, this is not the real benchmark, but it's more like a kind of indicator. So we get 100 milliseconds for the Awkward version on a single thread, and 1 millisecond for this dummy kernel. Of course, this kernel can probably be written in a better way, but this already seems to work okay-ish. Now let's move on. You know, we want to do more complicated things than computing the sum PT. How about the invariant mass of the jets in the event? Now here we do this in a kind of contrived way. Let's write a kernel that that again loops over the jets in the event. For each jet computes, or basically adds up the four momenta of the jets, and then computes the invariant mass of the jets in the event. Now I want to take to heart Nick's sort of call to action here, that don't write event loops, rather write functions that process parts of the event, because that's much easier to debug and much easier to make sense of. And this is kind of in the same spirit, but perhaps subverting a little bit the grand ideals of the revolution. So here we do loop over all the events, and we do more than one thing within the loop, but we still keep to a sort of single short idea. So the idea is add up all the Cartesian four momenta of the jets and compute the invariant mass. So I won't go over this code here line by line, but it should be familiar to you in general, because it's basic Lorentz Lorentz vector algebra. In the end, we compute an invariant mass for each event, and we put that into the output array. That's kind of the core. And you see here an example use of CUDA device functions, which allow you to essentially call from a kernel another function which is not itself a kernel, which essentially just allows you to factorize the code a little more. So that function can only be called from within the kernel, not from the CPU. Okay, so let's execute that. And let's run that on jet for momentum data. So spherical to Cartesian, let's print out the invariant mass values. So here it is. It runs. And again, I verify that against the CPU implementation. Of course, one would like to not do this by hand, sort of writing the maths by hand. So one can imagine wrapping this in a device agnostic way in a library. Now, we can also create a simple histogram from these values using QPy built-ins. So we have qpy.histogram, which works exactly as NumPy histogram. And crucially, we need to make sure that we use float 32s also for the bin edges. Otherwise, you might have a silent slowdown. And let's plot that histogram with our favorite plotting library in matplotlib/hep. Okay, and there we go. So one can do simple histograms directly using QPy. However, typically we need weighted histograms. Unfortunately, they support it out of the box in QPy. So here we create our own method for this. This also serves as a good example on how to use atomic operations. So this is kind of what you will find in a typical tutorial for CUDA programming, how to execute as an input the data to put into the histogram, the weights for the data points, the bin edges, and then we have the output array for the bin contents. Now we remark here that we make this two-dimensional for reasons I will explain in a moment. And we have the output array of the weight squared, which we use to then compute the error. Okay, so we do a similar one-dimensional loop over the inputs as we've shown before. And we also take note of the block dimension. So basically what we want to do is for each data point, we want to look up where it should be in the histogram and then fill that into the right bin. However, then you have the case where multiple threads try to fill the same bin. This is not thread safe and will result in a wrong output. So we need to do atomic operations in filling the bins. So we use CUDA atomic add where we specify the array, the index in the array, and the quantity that we want to add to that array. And that takes care of the synchronization such that different threads would not fill the same bin at the same time. However, of course, that makes it slow and serial in that case. So what we do is we make a 2D histogram where we have in one dimension the bin indices and the other dimension the block index, such that at most in the same block we will have to synchronize, and across the blocks we fill different histograms, and then we add the output data up across the blocks later on. So this is kind of a technicality. And unfortunately, again, numba CUDA does not have a search sorted built in, so we kind of have to roll our own. So you see here the typical way that many things are available, but some things are not. In which case, roll, which may or may not be complicated. So sorted is fortunately not very complicated to implement, and I'm not going to go over the code here. You can do this, of course, in a faster way as well. We just show that it works. So here we create an array of 10,000 normally distributed numbers with weights of 1, and we fill it into a histogram from -5 to 5 with 100 bins. And we do this with the following block and thread size dimensions. So here we create the histogram outputs, which are initially 0. Then we fill the histogram, and then we synchronize. And finally, we get our one-dimensional histogram by doing an excess sum and transfer the result from the GPU to the host or CPU memory using QPy as NumPy. So let's run that. Takes a moment. And now let's plot the QPy. Okay, so first let's here I plot just the QPy histogram versus the NumPy histogram, the built-ins, and you see these give the same result. So that's great. And now we compare the NumPy histogram to our custom weighted histogram, and that's the same too, except that we have also errors available now thanks to the weights. Okay, and let's test the speed of that histogramming function. So here I wrap the histogram synchronous in a single function and just run that. Okay, so about 1 millisecond per loop, and this one is less than 1 millisecond per loop. So GPU is slower in that case. What gives? So the thing is, we are running this on a rather small array, just 10,000 elements. So this means that the cost of doing business is higher than the business itself. So let's make a bigger array and run that again. And then we should see the GPU outperform the single-threaded CPU. So about 1 millisecond for the GPU and 70 milliseconds for the CPU. Okay, great. So now we are moving towards the end, sort of putting it all together for a more complicated example. So I took the liberty of taking the exercise from the analysis description languages benchmark GitHub. Many thanks to the people who put this GitHub together, or this kind of exercise. I think it's super useful. So in no way I take credit for the work done there. I kind of just take this as a building block. So what we want to do is plot the sum PT of the jets, which have a PT greater than 30 GeV that are not within a delta R cut of any lepton, which has a PT cut as well. So that's a typical thing we might want to do. Now, basically what we need is a kernel that does delta R masking, and I've written it here. I won't go over all the details of the code, but you see it's maybe 20 lines or not too many lines at least. And basically it works in the same way that we loop over all the events, and for each event we do something. So what we do is we loop over the first collection, and we get the eta phi of the object in the first collection, so the jets, for example. And then we have a nested loop, which is of course not the most optimal thing, but again, starting point. In this second loop, we loop over the second collection, and we take the eta phi's of the second object, we compute the delta eta, delta phi, we check whether or not it passes the delta R cut, and in case yes, we fill the output with a mask essentially. So this is pretty standard, what you would really naively write in kind of a root, but we can write this in numba and run it on the GPU just to see how it works. And we have the same sum function as well from above, except we've only added a masking, which allows us to skip the jets which don't pass the cuts. So let's run that. Okay, and now let's take the jet for momenta and muon for momenta from the events, and let's first mask the muons that we want to use and mask the jets that we want to use. So we apply the PT cuts, and let's create an output mask which is initialized with zeros for all the jets that we will fill with a delta R mask. Okay, and now let's call the delta R function with the inputs. So basically giving all the jet for momenta our parameters of the delta R cut and the output, and call CUDA synchronize. And then we create the final mask from the jet PT cut and the delta R cut. So you see, you can still run this functionally. You don't have to write a big event loop. Of course, it's not the most elegant, but it's also straightforward to do. And now we have our Boolean mask of the selected jets. Let's just check what it looks like. So this is for each jet, there is a Boolean. So this is a kind of flat array, but we can interpret it with the same jagged structure as we had before. And now let's compute the sum PT of the selected jets in the events. So we have our sum PT function. We have the jagged structure, the jet PT. We have, what's this? I forgot. Mass grows. Aha. So do we want to skip any events? No. So let's use all the events. And let's use just the selected jets and put the output in this array. Okay. So we should have our sum PT. Let's just print it out too. So here we go. Zeros are for events where no jet passed the cuts. And now we can fill this into the histograms in the same way. Let's apply an event cut as well based on the sum PT. So we can plot the histogram. And there we go. So this is kind of the end. What I've shown you is how you can use numba to write simple CUDA code for an NVIDIA GPU, which can be useful in certain cases. So we've seen that certain mini benchmarks can be much faster than a single CPU thread, which of course is not the final say about which is the most cost-effective device. But in case you have a bunch of GPUs available and your data sizes are on the order of sub-terabyte, so on the order of maybe 500 gigabytes or so, such that you can effectively load this all into the host memory in a short amount of time, or at least iterate through it fast, such that you're compute limited. You can use a GPU to process your data fast, especially if you want to vary the parameters while keeping the data the same. All right, so that's it for my materials. I don't know how I'm doing with time, but I'm happy to open the floor to questions. Okay, so here, let's see. First question, how do I choose the number of blocks and threads? Essentially by trial and error is what I understand. So what I know about this is that in the NVIDIA workshop where they teach you to do these things, they have you try all the different values and see which is faster, because this depends on the device and these kind of things. I don't think this is really a very educated way, so there must be something better to do. But in my case, I found maybe 20% improvements from messing around with the number of blocks and threads, not the factor 2. You can use one block, one thread if you want to check that you don't have any race conditions. So that's another point. Okay, let's move to the next one. Can we use this for maximum likelihood? I didn't try, but I suppose you could. Although I think you want sort of probabilistic or like library that has more built-in probability distributions and things like that, which I think TensorFlow provides quite nicely. So this could be an option, but I think there are also other options.
Yeah, if I may just a second. Yeah, just on this one thing, actually there will be at least one presentation in the week about
yes,
this.
I saw. Yes, that's a good point. Yeah. So yeah. Okay. Just stop me whenever I'm over the time or anything like that. I'm not sure how I'm doing here. Let's go on with the questions. Can we use shared memory as a kernel argument? I don't know. I haven't tried. This goes beyond my my experience. What about checks instead of QPy? I think that's a great idea. Checks is purely functional though, so you cannot write these kernels by hand as I've done, which may make some things a bit more complicated, but which opens you up to running on TPUs and having differentiability. So it's a kind of trade-off, I guess. I think QPy is not dead yet. They will be releasing new versions still, despite the fact that the deep learning library shifter, or what was it called, chainer, that used QPy is not developed anymore. Is there a way to check if there is any race condition? Run the code with different numbers of threads multiple times and see if you get a different answer. So like with one thread and then with 1,000 threads. That's how at least I check. How do I remove the questions, I wonder? Okay, the first thing you did, selecting the GPU kernel. Oh, I see. The GPU runtime of the notebook. You don't need to do anything if you're running from a plain Python file. It just works by itself. So that's just the runtime means like which machine will the notebook connect to. That's a Jupyter thing. Is there any advantage using numba instead of PyCUDA? I did not try PyCUDA. I think it's more low level, as I understand. To me, the advantage of numba is that you can run kind of almost the same code on a CPU and on a GPU, and it's rather user-friendly. Can the overflow bin be omitted? Sure. I mean, that's up to the specifications that you want to follow. So here we chose sort of just the root specification. Is Pandas compatible with QPy? Not out of the box, but there is, NVIDIA has released a whole ecosystem of libraries called Rapids AI, which has a Pandas replacement that runs on the GPU. I haven't tried it. There is a search sort of implementation in Thrust. Yep, that should be good to use. Yeah. Okay.
So we good?
Yeah. Thanks so much.
Yeah. Well, thanks very much for